more you question.
Yes.
Okay, so thank you very much for having me. For me, it's a good opportunity to share what we've been doing in our collaboration with the GMT. And I am Tiago. I am a postdoc researcher on the astronomical instrumentation of the University of São Paulo, Brazil. And let's dive in. Okay, so probably most of you know about this because you are one of the institutions which have lots of partnership with the GMT, one of the founders. But I'm going through some of the GMT stuff very simplistically. Actually, I'm not going to enter in some details, but just to give an overall what are the instruments of the GMT and what are our group contributing to it. So the GMT, as you know, is a major American and universities collaboration, which started in 2003. And I think in 2005, they extended it they extended it for other partners around the world. And the state of São Paulo founding research is one of the contributors. Usually we call it that Brazil is contributing, but actually it's only the state of São Paulo. And we are working, the PI of our group are working in order to gather more federal money to join extra to these projects as well. So far, we have donated $55 million. If you consider the whole project, it's a small amount, but for a single project, it's a very huge amount of money. And this allows the Brazilians, astronomers and engineers to work along with as a partner for the instruments which are being developed. And as this grant was approved, we created our own association related to the GMT, the Brazilian Association. We have a website, you could check it out later if you want. And also, there is a spin-off that coming from this project. So it's a company, it's a non-profitable company which it's operated in Brazil. And it's basically a gather of engineers, mechanical, electrical engineers, optical engineers as myself, astronomers, and system engineers. So we are gathering the several abilities which are necessary to build those instruments and to contribute to building it, and also to extend it after the instrument's been done. If the goal of this company is to being able to extend for other fields which also demands this kind of abilities. So our project was approved in the end of 2014. And as I told you, it's a São Paulo state contribution. The Institute Steiner, so it's University of São Paulo, the astronomy institution of this university, and also the spin-off Institute Steiner, which is named after our deceased professor, Professor João Steiner, which was one of the icons of our astronomy in Brazil. He has many works related with dark holes and galaxy formation. So the GMT, basically, there are seven. The primary mirror, it's made of 7 mirrors. Conjugate in the second, it's conjugated mirrors with the first. And this is a unique design because the other ELT, they are composed of many other mirrors. And this choice was made in order to simplify the design. And also because only the mirror carriers laboratory was capable to produce such a large mirrors in this configuration. So it's a unique telescope which has some characteristics. It's a Gregorian. It could span up to 20 arcminutes of, it's one of the broadest of field of view. It goes from the optical to the infrared, to the middle infrared. And okay, the primary mirrors has around 8 meters. The primary is around 1 meter. It's an f8 with a plate scale of 1 millimeter per arc second and with a higher resolution, including AO. So the GMT are gonna host several of first slice instruments, which are going to be split in 2 sections. The first one is the Gregorian focus, which are going to be seen and also GLAO limited, so ground layer adaptive optics. And so it's predicting for the first slide some of the instruments. So there is the Gregorian platform and also the fold platform, which are going to host the diffraction limited instruments for this telescope. And also there is the high resolution spectrograph, which are going to stand on the platform, which is gravity invariant. I'm going to talk more about this in a minute. So one of the capabilities as well of the GMT, besides of the 2 platforms for the instruments, is to include ADC for the Gregorian and focus, which are going to span from 10 to 20 milliarc minutes of field of view. So as I heard, I'm not sure about this, but apparently there is 2 sets of ADCs which are predicting, and they could be deployed from the instrument as the science demands required. And I think it's good to highlight as well the M3, which are going to take a smaller portion of the field of view, which are going to the diffraction limited instruments. And one of the peculiarities of this M3 is because it's going to be used only for some of these diffraction limited instruments. Some of them are using their own way to acquire the image from the telescope without using this M3. So this is the partnerships which we are currently on with the Steiner Institute and our university. So there is one of the instruments is the CONCAM, is the commissioning camera, which are being developed by the Carnegie observatories. And we have some partnership here, mainly with mechanical and system engineer and electrical as well engineers. The manifest, which is an instrument which are being built by AAO Macquarie at Australia, GCLIF and GMACS, which are both both spectrographs. GCLIF are going to be the precision radio velocity spectrograph, and GMACS are going to be a mid-range spectrograph and both of them are being developed in Harvard in the Center for the Smithsonian Astrophysics in Harvard. The AOTC, it's another instrument. It's a test bed which are going to be built in order to test the AO capabilities of the telescope before we put in the instrument. It's like the CONCAM. CONCAM, it's also a camera which are going to be deployed in order to test some of the ground layer capabilities, but it could be extended for some science as well. Okay, I almost forgot to mention, we are starting a collaboration as well with the guys here from University of Arizona, Extreme Wavefront Control Laboratory. And basically it's to contribute with the GMACS. Maybe you guys could confirm, I don't know if it's gonna be a first light or first light instrument as well.
That's the hope.
Yeah.
That's the hope.
That's the hope, okay.
Yeah.
Yeah.
It's not official. Yeah.
Okay, yes, but probably it's going to be one of the first light instrument as well. So this is going to be the disposition of the instrument. So GMACS and Manifest are going to be in the Gregorian platform. And also we have the GCLIF, which is in the invariant, the GIR, the gravity invariant rotational platform. And the diffraction limited instruments, which are, there is 2 spectrographs, one of them with image capabilities, which are the GMTs and GMT nears, which are going to be in the folding port platform. And also GMACS are going to be in one of these platforms. So let's discuss a little bit of the capabilities of each instrument. So the commissioning camera, the PI is the Jeff Crane in Carnegie. It's a visible camera basically built in order to test the image capabilities of the GMT prior to the instruments arrived. And it has a smaller field of view, 6 arc minutes. It's one of their goals as well is to produce some images for scientific, I'm so sorry, public outreach as soon as possible in order to increase the telescope's popularity along with in the media. But here there is an example of the optical design I included because I'm an optical designer, but we did not contribute it here. We are contributed with the mechanical assessments, so the structure and the assessments for flexuring, also the electrical components and how they would be assembled as well. We are contributing, and with system engineering as well. So it has already passed its conceptual design review, and it's about to be completed. I think it's not, maybe April, it's going to pass through its preliminary design review. I heard that this instrument as well was not fully approved. I don't know the status. I don't know if it's going to be, if really are going to be built or not. It's still, I think there was some debate about it, but hopefully it will. And the GCLIF, it's one of the instruments which are already done. It's passing through some testing right now at Harvard. So prior to go to the GMT, it's going to be deployed on the Magellan Telescope in order to test it and to see if everything is going along with which predicted. Its PI, it's Andrew. I'm so sorry, I don't know how to pronounce his surname. But he has a long-term partnership with our institute as well. He went there several times in order to lecture, and we have one of our students. It's contributing with exposure time and calculator, the software, and one test bed as well. So it's made to test precision radial velocity of the stars of some systems, and it has these characteristics which it's going to acquire the GMT light through this robotic arm, so it's on the environment, it's on the GIR, but it has this arm which are going to be inserted into the folded port. It has a mirror which are going to direct the light into some fibers, and the fibers are going to be the slit of this instrument. So this is how the slit of this instrument are going to be are actually in reality, because it's already done, except the manifest part. Manifest is still under construction, but it's already predicted as well. The manifest would provide light through a set of fibers as well. So it has several fibers, diameters, and characteristics in order to be able to vary the spectral resolution of this instrument in high precision, high throughput, or medium throughput, and non-scramble and precision radial velocity of the targets. There is the mechanical model and the optical model as well. So the slits are going to be right here. It's an HL spectrograph. It's going to be collimated on the HL grating right here. Actually, there are two of them, one aside each other. And there is a slightly misalignment in order to the light come back and being picked up by a prism right here, actually a main mirror, and then we split the light between two cameras, blue and red camera indivisible. And one of the contributions with one of our student, graduate student have done, it's published on this SPIE proceedings. So he planned, he made a software and a test bed for an exposure meter. The GMACS are going to be the multiplex, not multiplex, multi-object spectrograph for the GMT. They say that it's the workhorse. It's going to be the most robust. It's going to be able to produce most of the signs of the GMT. And it has a huge participation of our group as well, including optics and the mechanics, electrical, system engineer, everything. We have a very strong and long-term partnership with the Harvard Smithsonian on this project. It was initially on the ATM, Texas AAM was responsible for this instrument, but after it was exchanged for Harvard, and our group is participating in all this process. So we participated from the conceptual of this instrument as well from the PDR, which just happened in the beginning of the last year. So there is a paper which is about to be released. It was already approved, and you can read more about this as well completely. It's a huge paper. And it's basically, it has two cameras as well, a blue and a red camera. There are going to be some cassettes where several slit masks could be inserted on this instrument. It's going to use some, these are the places for two volume diffraction gratings. So they could be exchanged as well, depending on the resolution that the science demands. There is several of them. The GMACS has a particularity as well that it could be used as an image, not very good resolution, but could be used as an imager as well. And aside from the VPH, there is also binary gratings, and the other one, which is the two-saw, I forgot, glazed gratings as well. Okay, so
are there multiple slit masks on this? Like there's a slit mask exchanger?
Yeah.
Okay. Wow.
So during your run, you could change by the slits. And the slits are multi-objects, right? So you could place several targets that could be collected at the same time.
So is it like prepare one slit mask while you're observing a field? The other one can prepare in the background, or you have to set them?
You are going to set your targets. You could use the ones that are done, or you could make one manufacturer, several of them manufacture, and put in them on the cassette to be used during your run.
Oh, okay. I'll ask at the end of the talk.
Okay. What else? So there is. This is one of our strongest collaboration, and here is just to see the dimension of this behemoth, which is it's massive, it's gigantic. Okay. And as I told, we work a lot on the optical design of this. Mainly my colleague, which is Rafael Ribeiro. Now he is a professor in our institute. He made, along with Daniel Fabricant, the optical design of this instrument. I collaborate in some parts, make some assessments and tolerance analysis for these optics. Another thing that we are collaborating as well is to produce the mechanics for putting the instruments on the telescope. So this thing, it's massive. It's going to be built in a horizontal position, but it works in a vertical. So there is this structure which our engineers are helping to design, which are going to make this changing and putting them on the telescope. And hopefully this is going to be used for the others direct Gregorian instruments as well.
Yeah. What is manifest there?
Okay, we are going to be there.
Okay.
It's the next slide. Manifest, it's not the instrument by itself, but it is a facility which are going, because both of these instruments, these spectrographs, as well, the diffraction limit, so the GClef, for sure, the GClef and the GMACS could be fed by fibers. And manifest, it's going to be a facility which are going to, so I will try. So it's being designed in the AEO Australia, the PI, what had happened? Okay. John Lars is the PI of this instrument. So it's a fiber positioner. So there is several of these fibers which could be arranged by these robotic arms on a plate, which are going to be in the direct Gregorian focus. So several of these fibers could be acquired, could be positioned at the same time. This is just one example. There is a multitude of, a variety of fibers which could be placed in the field of view. And these could distribute fibers and could be used both of the spectrographs at the same time and also with different characteristics. And another things that the manifest adds to the spectrographs, it's because the spectrographs has a limited field of view, which does not span the whole 20 arc minutes of the GMT. But with the manifest, the spectrograph could be used in this whole field of view. It went through its conceptual design in the 2024. As I know, currently they have changed the strategy. I don't know if I've heard about, but it changed the strategy of the fibers positioners. Now they are using these robotic arms in order to place the fibers where they want to set up. But prior to this, the concept was the Starbucks, which was some fibers which were glued in some plate, in some glass plate, and they could walk through this plate against the gravity, and through some piezo mechanism, they could some sort of walk and be positioned in the real time at any time. It's much more faster than this one, but the big thing for this kind of concept, it was tested on the earlier instrument made by Macquarie, the Taipan, and apparently something goes wrong and they changed. It was not as good as they predicted. And there were also because on the Taipan, the things go with the gravity. So the risk was less than goes against the gravity, because if one of these piezo devices, which was they glue it with a vacuum pump, if they fail, they could collapse and affect other fibers as well. So the risk was too high. Then they are trying to mitigate this fact. So it has multi-object capabilities as well, of course. And what we have done on this, contributing with this instrument, is to design and manufacture the filter box of which is the interface between the manifest and the G-clave. As I told, we are going to have an ADC, the manifest, which are going to be here, and it could split the light between the manifest and its several modes and also G-clave. Manifest, it's going to be a directly out, but G-clave demands a filter box, which are it's a bit more complex than a simple filter box because it's going to be related to the modes that the G-clave could access. So it's going to be it's going to be 3 modes. There is several filters. Some fibers could pass directly to some of these filters at the same time. And we made the optical design for this, which could be one single relay of optics with which is fiber fed. So the fiber are going to be attached in some rod lengths, collimated, pass through the field, and then inserted, put it in the fiber again. Or several of them could be made at the same time using a relay made by 2 what is the word?
Translator rays.
Translator rays. Yeah, thank you. And also the mechanical design of this filter wheel as well has some complexities, has some which was designed by us as well. Actually, Rodrigo, which is here, which is visiting us, and he was the mechanical engineer responsible as well for this design.
The filter wheel is on G-clave.
Yes, it's on the route of between manifest and the G-clave. Let me just, so this filter wheel are going to be attached at some place here. So it's going to pick up some of the fibers of the manifest and then going to be routed in G-clave after passing through this filter wheel. They rather that the fibers could directly to the, it would be simpler, but there is no way to select several filters because let's see if I could explain. Because the idea is if I choose some set of the fibers for a specific mode of the G-clave, with this filter wheel, I could change between several filters looking at the same object without having to exchange between other fibers or. So this is the main goal. You could to expand the capabilities or without having to move the object by itself or changing fibers.
I'm just surprised the filter wheel is not inside the instrument and it's outside the instrument.
Also,
because I mean, I was working with Liger team and their design, and their filter wheel's like inside Liger. So I was just surprised to see a filter wheel outside the instrument feeding it.
It was fiber fed as well?
No, this is just a completely different instrument.
Okay,
so
okay. Okay. It's because it doesn't matter because the fibers go to the G-clave, which are vacuum sealed. And yeah, it's a long way to go. Do you remember how long is the routing of the fibers? 6, only that? I think it was more, but yeah. So one of the things that we have to control is not to lose the light from the fibers when they are acquired, passing through the fiber to the filters and going to the. There is another parameter which has to be assessed as well, which is the focal ratio degradation of these fibers, and it depends of how much the fibers bend along the way. We are going to work on this as well. I think we are, right? Yeah. And to talk about the AOTC, which is the test bed which we are contributing as well, I have to speak a little bit about the GMT adaptive optics. So the secondary is going to be the mirrors with the actuators. So this is more or less the diagram. The GMT are going to have natural seeing and ground layer, which are going to be assessed by the directed Gregorian instruments. The folded ports are going be able to assess as well natural guide star and laser tomography. This is more or less the diagram, right? So the instruments here are going to be natural seeing or ground layer. And the instrument that goes on the folded platform will directly some of the light, the visible light, to the MGWS sensor, and as well for the LTWS sensor as well. And internal of each instrument as well, there is the necessity of some assessments of some of the adaptive optics has to be assessed as well inside of the instrument. There are going to be some wavefront sensors, basically in order to measure any misalignment that could happen between the instrument itself and the external wavefront sensors, and for the majorly for the LT mode, which is not able to measure some tip tilt, for example, of this guided star. So internal of the instrument, they need to have some assessments of these modes as well. And here is just a setup of how the ground layer works. It's the AGWFS. It's the acquisition guiding of the GMT. So some of the light which are not picked up by the M3 or by the instruments which are in the Gregorian platform. Some of the light are going to be picked up by a set of 4 mirrors and going to be divided by this 4 equal. There is 4 equal sensors which could assess nearby stars in order to expand the field of view and make the corrections of the atmosphere in a ground layer. So the PI of this is project of Harvard's as well, and the PI is I forgot his name.
Brian McLeod.
Brian McLeod. And on the right, there is a mechanical CAD view of the sensors which are going to be attached on the diffraction limited instruments, the MGWS and the LTWS. I think the only exception is the GMACS, which are not going to use those sensors. This is going on the GMTs and the GMTs. So we are not contributing with those 2 spectrographs, but just in terms of completeness, I'm showing them here. They have their own science objectives, and they are the GMT. It's a partnership between the University of Texas and the CASI in Korea. The GMTs are being designed by the another Australian university, Australian National University. And as I said, inside of the GMT and the others as well, they have some internal wavefront sensors, which are necessary to make these assessments. And the EOTC, which is the instrument which are collaborating, and it's a cost reduction version of these on wavefront instruments, which are going on these diffraction limited instruments. And the goal is to be able to assess the EO capabilities of the telescope, see if everything is working prior to the instruments to arrive on this way, and also make a test of everything, the control, and etc. So one thing that we are collaborating is to make the whole mechanical setup. We are contributing, not the external wavefront instrument, but the internal part. And one important part is the holder of this entrance dichroic, which is a bigger one. So this is a 250 millimeters dichroic. It has some peculiarities of the mechanics which has to be made in order to avoid any stress on these optics. So parts of the visible light, most of the visible light which arrive from M3 reflects on this dichroic, goes into the MGWS, which has some pyramids in order to assess the EO of the natural gas star. And just here we have another vehicle which are going to direct only the light from the laser guided star, which I think it's 530 nanometers. Just a small band are going to the LP wavefront sensor. And this is the optical design of the AOTC, which I'm the one responsible for it. So, these IRs only 5% of the feeds are going to be transmitted by this dichroid, which are going into acquired camera, which is necessary in order to center the light on the detectors on the instruments sensors with a broad field of view. So these acquisition camera are going to have 20 arc-second of field of view. And each the science camera, the scoring camera, and the other sensors has 1.8 milliseconds of field of view. So it's very small. And it's small because we just need it for testing the AO capabilities. So the instruments itself are going to have a broader field of view. But so the acquisition camera, it's useful for centering the telescope on the field of view. And it's used up to the H band for a focusing tool, which are going to measure the focus of this instrument and some small order aberration through a Schwarz-Hartmann. The scoring camera, which is on the H band, are going to assess the strain of this image, and the TTPS are going to. It's important as well because it's measuring the tip tilt of the guided star. Plus, it's going to have a phase retrieval algorithm for the mirrors of the telescope to narrow down the error of the phasing of the telescope. And another use for the AOTC is to test the secondary mirror, which are being built in Adi Optica in Italy. And actually, one of our concerns is to produce a instrument stiff enough in order to build it in the US, transported it to Italy, and then to Chile after these tests without many interjections during the way, without losing alignment or so something robust. And this is just a summary or a gather up of the science goals of each of one of these instruments. We could check it out later or discuss with more detail. So that's it, guys. That's what I have to present.
So before you send the AOTC to Italy, it'll be built in Brazil and then sent to Italy, or will it be built at GMTO?
Not sure yet. There is some hope that it could be built in Brazil, but it was not decided yet. I think the drawback that I think we are not be able to overcome, it's because some of these optics, we did it in a way that it's simple optics. So it's all refractive in order to reduce the complexity and the cost as well. So it's very small optics, around 1 inch or 2. And only this one, which is bigger, which is around a bit more than 2. But this we could manufacture. But the larger one, much larger than this, I think we don't have a company to do it.
Do you know why, like on this camera, the focus and truth sensor is J-band and the tip tilt piston sensor is H-band?
Okay.
I thought it would make sense to have them all in the same band if they're all doing like some kind of AO correction. No? And this might be just like a design choice. I don't know.
It's a design choice. Let me come back a little bit here. Let's see. On the instruments, they are going to use the H-band for actually the signs of this instrument in the K-band. They need to be fire cooled. And the other instruments are in the K-band, the TTPS in the K-band, and the FTS in the H-band. In order to decrease the cost and avoid the complexity of having a cryo-cooler, because we don't need it, it's not a science instrument, we lower a little bit these bands in order to avoid those risks and cost. But why? Let me try to think about your question again. Your question about because on our design, the scoring camera, which are going to assess the straw, and the TTPS are both in the same band.
Okay.
Only the FTS it's in a lower band. And one of the objectives here is to reduce the non-common path aberrations. So all of them has the same field of view, has a common field stop. And it's a way to maximize as well the throughput of each channel, in order to not split the light between them and focus with just one part of the light for one sensor and maximizing the light that are going on the other sensors.
Oh, okay, that makes sense. Yeah.
Any question online?
You know how many slits you can put on GMACS? Like how many objects total?
I don't know, but it's a lot.
Ballpark? Like 100?
Yeah.
What was the total field of view of GMACS?
The GMACS,
7x6 arc minutes.
yeah,
Oh,
but
Insane.
only the GMACS. With the manifest, it could be expanded.
And it also said something about mini IFUs on GMACS?
Yes, manifest could could allow the GMACS to be a IFU spectrograph as well. GMACS.
so are all of these instruments going to be on the GMT at the same time, or are they like one instrument goes off, one instrument goes in?
Okay,
How many can be on the platform at the same time?
with manifest you could use both of them. Okay, here. When it's used only the instrument by itself, only one of them could be used by time at time. So the GMACS could be or the no, this is not an instrument, right? But only the GMACS could be inserted or deployed from the direct reverberant platform, and the other instrument cannot be used during his. But with the manifest, we could use as much as the GMACS, the G-clef, and other fiber-fed instruments as well at the same time, using different fibers, using it.
Okay.
When used only, the G-clef, as I said, it has a robotic arm, which are going to be in the field of view, so it could only be used by itself in its nature or in its I missed the words, but in its nature configuration, no.
Base configuration?
Yeah, it's in space configuration.
They're all fixed, okay.
Yeah, all the
folded ports.
The diffraction limited instrument, I think they could be only used one at a time as well, because the M3, the native M3 of the telescope are going to turn to direct the light into each of these instruments. But the GMACS as well are planning its own tertiary mirror, because it must be, as it is an extreme AO instrument, it must have some special, very stiff M3, which apparently it's not the case of the GMT M3. Which is, we hopefully, Rodrigo as well, are going to start to collaborate with this effort to make this tertiary mirror for the GMACS.
So the AO camera you mentioned, is that available for all instruments there if it's just picking off light?
The AO camera it's going to be the test instrument. So it's going to be deployed in one of these platforms, test the whole AO system with the external wavefront instruments, which are going to be the definitive ones. But when it's accomplished its goal, it's going to be removed, and the external wavefront instruments are going to one of the diffraction limited instruments, and it ends its lifetime.
Okay.
Any question from anyone online? No, thank you everyone for coming.
Build a Perl cluster science case.